please hit subscribe.
We will now apply the test that we have developed on ratios to special kinds of sequences called series. Let us consider the following sequence. Let's say the first item or term in the sequence is as follows: 1 factorial over 2 plus 1 factorial or 3 factorial. Then the next term is the following sum. That is the first term, which is 1 factorial over 3 factorial, plus a new term, which is 2 factorial over 5 factorial. Then the third term of the sequence is such that it is the previous term, so this is a sub 2, plus a new term, 3 factorial over 7 factorial. And in general, we can write it as follows. The nth term is such that we have the previous term here, plus the nth term of a sequence. So we can see that this term, this term, this term, they also form a sequence themselves. And so the general form, the a sub nth term, is such that it looks like this. Or, if we write it using summation notation, this will be how it looks like. So, the nth term is the sum of the terms of a sequence b sub k from k equals 1 to k equals n. And bk here is another sequence that is defined by this expression. So, this is what we call a series, which is just a sequence. As we see, we have a1, a2, a sub 3 up to a sub n. So it's a sequence on itself. And the terms in the sequence are sums of another sequence. So here we have the sum of b sub k. So this is what we mean by a series. Now we want to know if a given series converges or diverges. Can we use the ratio test to test for convergence? So in the previous video, in a previous video, we actually used the difference test to check for divergence. And here we will try to consider using ratio test for the test for convergence. If we try to apply the ratio test for sequences directly, what we will get is the following. So here what we did is just substitute this sum for a sub n plus 1 and substitute this sum for a sub n. Then we expanded b sub k and the same here. Now what we see is that this expression is rather difficult to evaluate. And so it looks like it may be hard to use the sequence ratio test directly. However, we can notice the following. The numerator and the denominator are consecutive terms of the sequence. And so as n approaches infinity, if the numerator converges, then the denominator must also converge, right? Because they are consecutive terms. And then, if the numerator diverges to infinity, so will the denominator, because again they are consecutive terms. So that means that either both of them converges or both of them diverges. And therefore we only need to check either of them. If one of them converges, then both of them converges. If one of them diverges, then both of them diverges. So here we will just check the denominator because it is simpler. So this is the denominator. Then we replace b sub k with the expression. And then we are left with this expression. And we notice, or we note that this expression here, this limit, is usually expressed as follows here. Instead of writing the entire notation of the limit as n approaches infinity, it is common to see the infinity symbol here as the upper limit of the summation notation. And by doing that, we can now eliminate k and replace it with n. So this expression and this expression actually mean the same thing. Now, we recall that to show that this term converges, what we can do is actually find another term that is greater than this and show that it is convergent. So if this term is less than another, if this sequence or series is less than another sequence or series that is convergent, then we can say that this is also convergent. Likewise, if we can show that this term is greater than some divergent series, then this term or this sum also diverges. So we've been using this from the very beginning to show convergent and divergent series or sequences. And the easiest way is to actually compare them with geometric series. Why? Because we know when a geometric series converges or diverges. For example, here we want a convergent geometric series. So that means we will compare this with a geometric series with common ratio less than 1. And here we want to compare it with a divergent geometric series, and so we choose a geometric series with common ratio greater than 1. Now the intuition why this might work is because the common ratio is, well, common to every consecutive term in the geometric sequence, but for the general sequence, that common ratio may not exist, but we can approximate that ratio, that common ratio, as we approach infinity for a convergent sequence. And what that means is that as we approach infinity, this ratio between two consecutive terms, it may not be equal to r exactly, but it may approach that r, that value of r. So that's the intuition behind why this comparison might work. And therefore, we can apply the ratio test on bk. So bk, if we recall, is just the inner terms in the sum. And this is to check for convergence of a sub n. So if you recall, the original goal is to check for convergence. We want to know if this sum, a sub n, is convergent. Then, to do that, we are saying here that instead of looking at the whole sum, we can actually look at just bk, the inner term of the summation notation, which in this case, in this example, is this expression. And the process that we went through is that if we want to check the convergence, first we tried to do the ratio, but it looks like this ratio is a little bit difficult to evaluate. But we realize that if the numerator is convergent, then so is the denominator. And if the numerator is divergent, so is the denominator. And so we just check for convergence either of the numerator or denominator. And in this case, we are checking for convergence of the denominator. And then, to do this check, what we do is, because for the general sequence, there is no general method to check the convergence or divergence of b sub k. But we know a general method to check the divergence or convergence of a geometric series, and so we can compare this with the appropriate geometric series. And then, when we have done that, we can now check the convergence of b sub k. So again, if b sub k is less than the convergent geometric series, then this limit is convergent. And if it's greater than the divergent geometric series, then this limit is also divergent. And so finally, we will just check the ratio of b sub k plus 1 to b sub k, and we take that limit. And that is just a normal ratio test for sequences. So let's demonstrate this using this example. So what we're going to show, or what we're going to try to do, is find this limit here, this ratio. And if you recall, this is just the regular ratio test. If this ratio is less than 1, then this sequence b sub k is convergent. If the ratio is greater than 1, then this sequence b sub k is divergent. If it is equal to 1, then we really can't say anything using this test. And then the significance of this entire sequence of reasoning is that whatever is the convergence or divergence status of b sub k, that is the same status of a sub n. So if b sub k is convergent, a sub n is convergent. If b sub k is divergent, then a sub n is also divergent. So that is the significance of this entire chain of reasoning here. So let's just do that. First, we're going to try to get this limit. So we just replace b sub k plus 1. So here's our expression for b sub k. And we do this, and then it's easy to see that a lot of terms here will cancel, and we will be left with this term. Now, if you are left with this term, then we can actually take the limit as k approaches infinity. And what we obtain is that we get 1/4. And this 1/4 is less than 1. And therefore, we can say that this sequence here also converges because b sub k converges. So this test alone tells us that b sub k converges to 0. That is from the ratio test in the previous video. And this reasoning here tells us that because b sub k is convergent, then so is a sub n. Now, we have to take note that b sub k converges to 0, but a sub n does not necessarily converge to 0. Okay, so it converges to some number, but we don't know if that's 0. And the reason for that is because this conclusion is based on this ratio test. But because we are using this ratio test here, this conclusion is only applicable to b sub k. For a sub n, we are not using this ratio test. We are just using b sub k and this chain of reasoning. And that's why we cannot say that a sub n converges to 0. We can only say that a sub n converges. Now let's do another example. Here we have k to the k over 2 raised to the k squared for our b sub k. And again, we will start by trying to evaluate this limit. So we just write down the terms. So b sub k plus 1 over b sub k. And what we did here, for example, is, so here we have k plus 1 as the exponent. Here we have k. So we want to match their exponents. So we factor out one k plus 1 term. So this is what we got. And what's left here is an exponent of k. And we have an exponent of k here. So we can use this form. Okay, if we factor out the k plus 1 here. And then here we just do the regular subtraction of exponents and expansion of this perfect square. So we get this limit to evaluate. Now, to simplify this evaluation of limit, we notice that this k plus 1 here, we can actually replace it with 2 raised to some exponent, right? So we know that k sub k plus 1 is less than 2 to the k plus 1. And it's easy to convince yourself. Or if you want to do it more formally, you can do a mathematical induction proof. But it's quite easy to convince yourself that for k greater than 0, k greater than or equal to 0, k plus 1 is just less than or equal to 2 raised to the k plus 1. Now take a moment to convince yourself of that, and when you're convinced, then let's just do this operation here. So what we did is we just separated the limits because we know this limit. The first part is just e, and the second part, so if you just subtract the exponents, we get this. The second part is 0, so we have e times 0, so we get 0. And 0 is less than 1, right? And okay, so even before we jump to that conclusion, we say that 0 is less than this limit that we're looking for. We know that this is non-negative, so we put that there, and then less than or equal to, so that's from here, then 0 again. So something that is between zeros is just 0. And 0 is less than 1, and therefore from the ratio test, b sub k converges to 0. And again, if b sub k converges to 0, then we can say that this term, a sub n, the series a sub n, converges. Let's just do one more example. So here we have an alternating series. So negative 1 raised to the k over 4 to the k. Again, let's just get this limit here, this ratio. And this is just expressing b sub k in terms of the expression here. And it's rather easy to evaluate this limit. It's 1/4, again 1/4 is less than 1, and therefore b sub k converges to 0, which means that a sub n converges. So what have we learned from this video? We've learned that, well, we've also learned this from a previous video, that a series a sub n is just a sequence of sums of terms of sequence b sub k. And we cannot directly use the ratio test on a sub n because it gets complicated. But we can use the ratio test on b sub k as an indirect ratio test for a sub n because of the following reasoning. So if we want to check the convergence here, normally we'd want to do the ratio test, but because this is rather complicated to evaluate, we just notice that if the numerator converges, then the denominator also converges. And if the numerator diverges, then so does the denominator. And so we need to only check one of either the numerator or the denominator. And normally we would choose to check the denominator just because it's simpler. Then we can compare this with the geometric series. So if this term here is less than the geometric series that is convergent, then this is also convergent. If this term here is greater than the divergent geometric series, then this term is also divergent. And so to do that, we just need to check b sub k using the ratio test that we've developed in the previous video. And that's why we just have to take this limit. So if this limit is less than 1, then b sub k converges to 0. That is what we established in the previous video. And if this limit is greater than 1, b sub k diverges. And when we have that, we can now say whether b sub k converges or diverges. And because of this line of reasoning, we can conclude the divergence or convergence of a sub n.
Please hit subscribe.